Now, in order to do that, what I should better try to do is to have a simple and small cache. Because a simple and small cache, then no associativity, and not very large cache, will potentially allow me to get a cache which will function in one cycle, then the hit time. If I go for associativity, I have to make comparisons, many of them, and most of the time I have to increase the cycle time, which may or may not have problems. There is here something which we call an XOR mapped cache. An XOR mapped cache, it's a trick which is changing a bit the way the transformation from the address in the memory address towards the cache address is done. What we do traditionally is we pick up a number of bits from the address and we use them to select a set in the cache. Instead of just using those bits directly, you can put some XOR between them to do a bit of manipulation in order to try to avoid conflicts. Then this is what you are trying to do. Then to make accesses which normally will go to the same set to be mapped to different sets. And in this way you kind of mimic the way associativity, but at low cost, because there are no comparisons. Okay. Now this is another trick, and somehow we put here the carriage in front of the horses, but presumably we'll understand the thing. Then a program, it's actually working in what we call the virtual address. It's the address within the program. You start from 0 or from wherever, and those are addresses which make sense in the program space. Your physical memory system is working with different addresses. Then what we usually do is when you issue an address, that address it's in the virtual space of the application, which is transferred first to a physical address, then it's going to the cache, and then it's going to the main memory. Then I have something on this road which takes time and which may be actually moved out. I can go for a solution where my cache, it's organized based on the virtual address. There is a translation anyway between the physical address and the cache. I have to do that anyway. Now, if I do that, the benefit will be that I am looking in the cache directly with the virtual address. If it is there, I do not pay any kind of time in doing the virtual address transformation. If it is not there, I am doing the transformation and then I'm looking in the main memory. Then what I did was postponing the calculation. Then I have a better hit time and I have a worse miss time. I took a transformation from higher in the transaction flow, lower in the transaction flow. Now, I can even do better, and how can I do better? I should prepare for the situation when I will have a miss. And this is the last thing. Then I am doing the access in the cache based on a virtual address. If I have a hit, I'm lucky. Then I get the best, time possible. I'm not doing that calculation. In the same time, I make a small investment. I'm preparing the physical address. I may or may not need it. This is in general called anticipated calculation. It's something which we use mostly in computer arithmetic in order to speed up calculation. That it's utilized in addition, but also in other kind of things. It's one standard trick. As I told you, computer architects have a limited toolbox set. This is one of the pulse that we have. Now, if I have a miss, I already have the calculation of the physical address, and I can go directly to the access. Then I have my cache organized on a virtual address, and if there is a hit, it's fast. I don't have the penalty of the transformation. I am computing the physical address while I'm doing the access for the cache, and if there is a miss, I already have the physical address done. Then somehow I managed to hide that calculation under the carpet, which is good, right?
Waste of power. Right?
Sorry?
If you don't need the calculation, then it's a waste of power.
There is, but you know, that's the misery of life. You don't get anything for free.
That is true.
Is that true?
Yeah.
Have you ever got something for free?
Only the sunshine.
No, it's not for free. You pay for that too.
Actually, you do, yeah.
Yeah, unfortunately. But maybe you are lucky. You know, Dutch people, they like a lot the concept of gratis.
Right.
True? You know, I was surprised to see that in Dutch there are a lot of words for cheap. Then when you say something which is low price, in Dutch there are many words to say that,
Goedkoop.
to indicate that things, you know, are more attractive. As they say in French, bon marché, which means good stuff, you know. But in Dutch you have a lot of things to say that, right? No, you don't realize it.
Goedkoop. Goedkoop. Gratis.
Goedkoop, wat is meer? Gratis. Okay, I don't remember now. That was a long time ago. Now I'm getting more and more Dutch and I don't realize those things. It's interesting the way foreign people are looking to your own language. They observe things which you are not aware of. Okay. Okay. Now, there is a small problem with this approach. And the problem is that each application has its own virtual space. And the same location in two virtual spaces actually is pointing to different places in the physical space. Then if I have only one process running, only one application, I have no problem. But if my computer is actually running a bit from here, a bit from there, then I have a problem with the cache. Because virtual address 1 from application 1 and virtual address 1 from application 2, which are the same in virtual address meaning, do point to different physical addresses. And then if I don't do things in a proper way, I have an interference between, you know, the applications. And there are two ways to do that. One is whenever you do a task switch or an application switch, you flush the pipeline, the cache. Then whatever was from the previous should go to the thing. That's kind of expensive because when you do task switch, eventually after some time you might return, and if some of my data, you know, I was evicted by another task, and when I return, some of my data, if they still exist in the cache, could be useful. If I don't do anything smart and I evict them, they are gone. And what I can do is to assign to each process an ID. And then when I'm looking in the cache, I'm saying, okay, I have a hit, but is this mine? Is this location associated to my ID? If it is associated with my ID, it's fine. If not, I kick it out and I bring the right one. Split caches. Actually, I think I told you about that last time, right? Then this is a standard approach which will allow me to deal with instruction and data in a different way. They have different kind of history, different evolution, and by assigning one cache for data, one for instruction, I am hitting two rabbits with one shot. Then, first of all, I have parallelism in addressing those memories because they are different physical memories. I deal with the iCache whenever I'm doing instruction fetch. I deal with this one whenever I'm doing, you know, memory execution, write back, depending on how I deal here, yeah, and bringing the operands, depending very much on the pipeline. But somehow I decouple them. That's one hit. And the second hit is because they have different history, the histories are not interfering. There is a separation. Then cache is based on spatial and temporal locality. The temporal and spatial locality of instructions is different than the one of the data. And now, I don't do that on level 2. I could have done that too, but do you have any idea why I'm not doing that? Yeah?
Too many caches?
It's too expensive. And there is something else. L2 has to be big. If I make it big in order to get the profit out of it, and I make it duplicated, doing specialization, it's not very effective. It's not giving me the full benefit. Specialization makes sense here in the small one. In the large one, I'm not really benefiting from that. It's not that it's zero benefit, but the real effectiveness of the approach is low. Then I'm investing a lot and it's not really paying back. My time is up.